So let's play with some bandwidth first, and then we'll discuss how these things work out. So I was here. I'm executing my code, saving, and then I'm going to do a bunch of histograms that I'm not going to plot with different bandwidth. So look at where it's specified. It's specified as an option, so inside the geome density thing. So comma, bandwidth is 1, bandwidth is 5, bandwidth is 10. And then I plot everything. So here are my different bandwidths. So this is with a 1 centimeter bandwidth, 5, 10, and 20. So what do you think about these bandwidth choices? Yeah.
It seems like it would be a bad idea to have the bandwidth extending beyond the range of the data. Like
yeah.
It shouldn't be ever above 0.
Yes, extending above the the range of the data. Well, sorry. You're making an argument about the edges.
Yeah.
Yes. So sadly, you cannot not have it extend at the end of the data, because however tiny the bandwidth is, you're going to hit the boundary at some point. So at some point, you're going to hit the boundary, but you're making a perfectly valid point, which is at the boundary, there is bias in a kernel estimation because you're having only half of the data. Because when you're trying to do your bandwidth for something that is a boundary, it doesn't see any data to the left, so it's only summing up the data to the right, so it will tend to go too high. That is something that is true with kernels. It's not a big deal because in the case of density estimation, because we know to be careful. But you're right that that's become very apparent when we have a very large bandwidth. So that's a good point. What does the bandwidth, like what happens when we go from here to here to here to here in terms of the shape of the curve and how it relates, say, to the underlying histogram?
Yeah. The bigger the bandwidth is, the flatter the kernel.
Yes, so flatter, we could say flatter, or we could say smoother. So as we are making the bandwidth bigger and bigger, the kernel is smoother and smoother. So you think this one is like bumping around a little bit. This one is like really, really flat. Intuitively, of all of this one, which one do you prefer? Or do you not like any of this one, and you prefer our original bandwidth, which is this one? Of all of the 4 in the grid plot and this one, which seems the nicer? This one. Yeah, I like this one too. So what's better about this one than about this one? They look similar, but they are a little bit different. And what's better about this one? So look, this one and this one.
Well, it seems a bit jagged here, right? Like it's almost like they're just forcing going through every sort of point.
So this one is a little smoother, and this one is a little too jagged. Doesn't seem a disaster in this case, but it still looks like it's a little too jagged relative to this one. And then, why do you prefer this one to this one? Or this one or this one? Yeah.
Well, the one with 20 bins, or the bandwidth of 20 doesn't seem to fit the curve very well.
Yeah.
Doesn't do a good job portraying the data.
So this one and even this one, it seems to be missing the height of the peak and to kind of overdo it a bit on the edges, and this one even more. So what happened here compared to the one that we have first is that it's over smoothing. So the first one is under smoothing. It's like really trying to go through every nooks and cranny of the distribution, and intuitively we feel that represents the particularity of my one sample as opposed to the underlying distribution that I'm trying to estimate from the data. So that's the under smoothing problem. And this one, and this one, certainly this one, and even this one seem to be over-smoothing in that they are not representing, they seem to be missing something about the distribution that is real, that is not noise. So that's the very similar to the conversation we had about histogram, is the choice we have to make when we are working with kernel distribution, which is the size of the bandwidth is going to determine how smooth the final project is going to look like, the final graph is going to look like. The tinier the bandwidth, the closer I am to what the data is in the data set, but potentially too close. And the bigger I am, the smoother things are going to be, but potentially too smooth relative to the real distribution. So if, for example, as Salim had said, the distribution seems to be, the sample happens to be drawn from a reasonably funky distribution, like the one I had shown you with the second bump. If I over-smooth, I'm going to miss that guy. It's going to try to force something completely uniform over things. If I under-smooth, it's going to do like. So in technical terms, what this means is that there is a trade-off between bias and variance. So the bias is the difference between what you're estimating and the true underlying shape of the distribution. And the variance is the difference between the true underlying shape of the distribution of the data generating process and what happens in reality because some noise got drawn or got added by life. Because I don't have a full sample of the world, I just have a partial sample. Okay? So the choice of kernel is going to be to optimize between bias and variance. There are various ways and a long literature to how we think about the optimal bandwidth selection to pick a point that is going to be satisfying between not too much variance and not too much bias. What typically all of this procedure are trying to do is minimizing mean squared errors, which is a combination of bias and variance, you're trying to minimize that. Of course, mean squared error is an estimated object, so you're trying to minimize an estimated object. So that's why you have to have some, there are various techniques to do it. We don't need to get into how they do it. The point is that if you don't specify anything, the reason why we prefer this one here is because we got lazy, we didn't specify anything, and ARC picked optimal bandwidth, which should serve you well for most of your application. But nothing prevents you to play a little bit with the bandwidth. By the way, you have different ways. There is a whole literature on calculating different optimal bandwidth. So as options, you can also pick another optimization formula for the bandwidth, or you can calculate your bandwidth size, or you can just leave it blank, and you're going to get a perfectly nice curve. You had a question, and then you had, no, you didn't?
No.
Okay. Alex, one of the, okay, go ahead.
Is there a way to quantify that trade-off between bias and variance?
Yes, exactly. That's mean squared error. So this is how, that's one way mean square error combined mean square error, which is the difference between your estimated function minus the true squared, combines bias and variance.
Okay.
Can you tell from that plot what the bin width is, or can you extract that back out from R?
Oh yeah, it can tell you. It can tell you what's you can report it as a. You cannot really make it from that curve, but you can output it as an output of R. Yeah.